If our universe was created in the famous Big Bang, is it possible that all forms of life also originated in an explosive event? Our world is governed by all kinds of cycles. Everything comes to an end and begins again, like the seasons that successively bring down the fruit of trees, whose seeds will give rise to new sprouts, bursting with vitality. And what if the same were true of the appearance of life in the universe? Could the origin of all existence have something to do with a cycle at the end of its course? Dear traveler, welcome. Today we're off to discover stars that have undergone brutal and spectacular transformations in the course of terrifying explosions. Neutron stars. Increasingly advanced research, thanks in particular to space telescopes, tells us more about these stars that have been dead for millions of years. Witnesses to cosmic history, these rare celestial objects invite us to explore some of the mysteries of astrophysics. Are you ready to unravel some of the secrets that distinguish these atypical stars? But before you set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! Long before the first neutron star was observed, the idea of the potential existence of this type of star was put forward in the early 1930s by Soviet physicist Lev Landau. This hypothesis came just after the major discovery of the neutron in 1932 by British physicist James Chadwick. But before we go any further, let's find out what a neutron is. A neutron is one of the three particles that make up an atom. An atom is made up of a multitude of electrons traveling around a nucleus, itself composed of protons and neutrons. The neutron is therefore a subatomic particle, which, unlike the proton, has a neutral electric charge. These two particles concentrate most of the atom's mass. Physicist James Chadwick discovered that the neutron has a negative charge on its inner core and outer edge, both separated by a positive charge, making the particle electrically neutral. This crucial discovery for scientists, for which he was awarded the Nobel Prize in Physics in 1935, opened doors in many fields, including astrophysics. From then on, after physicist Lev Landau put forward the hypothesis that stars could be composed essentially of neutrons, two other scientists worked on this concept. Still in the early 1930s, more precisely in 1934, Swiss astrophysicist Fritz Zwicky and German astronomer Walter Body, having assimilated that atoms are composed almost exclusively of vacuum, then made a disruptive suggestion. They imagined that atoms, so tightly packed together as to obliterate the vacuum, could create a state of matter of extraordinary density. These two physicists had the intuition that a hypermassive star, having completely exhausted its nuclear fuel, in other words, a star at the end of its life, could, after undergoing a supernova induced by the collapse of the star under the effect of its own gravity, become this kind of celestial object. During this chaos, the outer gaseous layers of the dying star would be expelled into the cosmos, leaving behind what looks like a naked star core. This extraordinarily compact and dense core would then be composed essentially of neutrons. The concept of the neutron star was launched, suggesting that a mass equivalent to that of the Sun could be compressed into a space reduced to a radius of around 10 kilometers. However, the study of these potential atypical stars would only take off a few decades later. For a star to follow this evolutionary path, it must have certain characteristics. In fact, not all dying stars are transformed into neutron stars. The most massive of all give rise to stellar black holes. The least massive, i.e. the most common, become white dwarfs. For a star to mutate into a neutron star, it must initially have a mass of between 6 and 30 solar masses. These particular stars are more commonly known as ordinary stars. But before we had any idea what a neutron star looked like, we had to wait until 1967. The PhD student whose discovery was appropriated by her Cambridge University professor Anthony Hewish detected PSR B1919 plus 21, a rather unusual neutron star. As you can imagine, the most common neutron stars are of such modest size that they could not yet be observed with the technology of the time. The star under study, on the other hand, not only rotated rapidly, generating a strong magnetic field, but also, like a lighthouse, emitted radio waves at constant intervals. This star, located in the northern constellation of Petit Renard, is in fact a pulsar, the first to have been detected and studied at length. A few months later, in 1968, a second pulsar was identified in the heart of the Crab Nebula, none other than the afterglow of supernova SN 1054, observed for 2 years since the year 1054, as attested by numerous writings from the Chinese and Arab worlds. The link between pulsars and neutron stars was thus established, demonstrating that neutron stars are indeed the result of a supernova explosion. The subsequent study of numerous supernova afterglows containing pulsars supported this conclusion. However, supernova afterglows have much shorter lifetimes than the period during which the pulsating emission of the neutron star can be observed. This is why the majority of pulsars recorded to date are not associated with an afterglow. Today, just under 3,000 neutron stars have been recorded in our galaxy, most of them, over 2,700, of the pulsar type. We'll be taking a closer look at the other types of neutron stars, which vary in shape and specificity. We can now affirm that these tiny, yet paradoxically extremely massive stars are in a class of their own. Since their discovery, scientists have noted that these unusual celestial objects are found in the same regions of the cosmos that are home to stars. Detectable neutron stars appear scattered across the Milky Way in the same way as all other stars, mainly along the disk of the galaxy. Like other stars, they can evolve on their own or form a binary system with a companion along the way. But remember, these stars are very difficult to spot, making it possible to claim that many of them are still lurking in the shadows. NASA estimates that there could be as many as 1 billion neutron stars in the Milky Way. In 2018, astronomers discovered the first isolated neutron star outside the Milky Way. They detected it while observing the Small Magellanic Cloud, 200,000 light-years from our Sun, and more precisely, the remains of a supernova explosion that occurred there almost 2,000 years ago. This discovery was made possible by the use of advanced technology. By superimposing the X-rays captured by NASA's Chandra Space Telescope with the visible light observed by the MUSE instrument mounted on the European Southern Observatory's Very Large Telescope in Chile, they were able to immortalize the remains of this cataclysmic event. In this fabulous pocket of gas, named E0102 and known for almost 35 years, they detected a second ring of gas. This one, much smaller in size, shelters a bright spot in X-rays, a neutron star. While the scientists weren't too surprised by their find, they were stunned by its characteristics. The star is surrounded by two gaseous rings, both highly asymmetrical and extending at different speeds. The main ring expands at a speed of around 1,000 kilometers per second, or 620 miles per second, while the smaller ring, that mainly houses the star, has a speed of around 90 kilometers per second, or 56 miles per second. Scientists are comparing the energy spectrum of this neutron star with that of two other well-known stars in our galaxy. These are located in the supernova remnants Cassiopeia A in the constellation of the same name, and Puppis A in the constellation La Pope, also unaccompanied by another star. The star, detected only by its X-ray emissions, emits no radio emissions, pulsed or otherwise, indicating that its magnetic field is relatively weak. Of all the neutron stars discovered to date in the Milky Way, only 10 others display these same characteristics. But what is of great interest to astronomers is to understand how this neutron star came to be so far from the center of the main ring, and why it is moving, albeit slowly. Astrophysicists are studying two scenarios. It could be a displacement or deformation of the vast shock wave following a series of precise circumstances leading to this asymmetry. Alternatively, it could be that the neutron star, rather than the gas pocket, underwent a sudden impulse after a strong, asymmetric explosion, propelling it to its present position. In short, this first extragalactic neutron star, although in the spotlight, has not revealed all the secrets surrounding the circumstances of its violent death. Let's take a closer look at the puzzling characteristics of neutron stars. These stars are exceptionally small, averaging just 20 kilometers or 12 miles in diameter. On the other hand, their density is extraordinarily high, estimated at nearly 1,000 billion tons per liter. By way of comparison, if a teaspoon of this class of star were brought down to Earth, it would weigh over 1 billion tons. That's why they're often referred to as the relics of all extremes. What's more, these stars have a particularly intense magnetic field. It's usually on the order of 100 billion teslas, the tesla being one of the units of measurement for magnetic fields. When you put it like that, I imagine you'll find it hard to imagine what this represents, which is normal. In fact, the magnetic field of a neutron star can be described as immeasurable, especially when compared to that of our planet. The magnetic field of a neutron star is on average 100,000 billion times stronger than that of the Earth. There's another surprising feature of neutron stars. Their surfaces are particularly smooth, devoid of any irregularities. This is all the more disconcerting, given that such dense objects generally exhibit extraordinary gravitational attraction, which has repercussions on their surface relief. A study of the prominences observed on the surface of neutron stars estimates that their highest peaks are less than a millimeter high. Proportional to the Earth, the tops of these mountains would not exceed 50 centimeters or 20 inches. With such a force of gravity, it goes without saying that life is impossible on the surface of such an object, which, although it bears the name of a star, is technically no longer one. Indeed, to be scientifically perceived as a star, it would still have to be capable of stellar nucleosynthesis. However, neutron stars no longer have the necessary resources, and are therefore considered to be dying stars. By the way, what is a neutron star made of? Like all stars, it has a multi-layered structure with varying densities. Let's start by dissecting the star's anatomy, by looking at its atmosphere. This is reduced to a thin gaseous envelope whose thickness can be calculated in centimeters. This first layer, sometimes referred to as a gaseous ocean, has a temperature of several million degrees. Gravity at its surface is 10 billion times greater than that of the Sun. Oddly for a star, this first envelope conceals a solid surface. This is the outer crust, similar in composition to the interior of a white dwarf. Composed essentially of iron, it contains highly ionized atomic nuclei and free electrons. The iron atoms form a sort of latticework, creating a crystalline structure. As density increases, fusion reactions between atomic nucleus protons and free electrons create protons. The result is a transmutation of the basic atomic nuclei, which then resemble nickel, zinc, or krypton, depending on their density. When the density becomes too great, the nuclei, themselves too rich in neutrons, let some of the latter escape into what is known as the inner crust. The inner crust is made up mainly of extremely neutron-rich nuclei, bathed in a gas of neutrons and free electrons. The entire outer layer, divided as we've just seen into two zones, is around 1 kilometer or 0.6 miles thick. Below this limit, the density becomes so great that the atomic nuclei have completely disappeared, gradually dissolving. All that remains is a superfluid neutron soup, mixed with a small quantity of protons and electrons. This zone, approximately 10 kilometers or 6 miles in size, corresponds to the outer core of the neutron star. As the proton gas is superconducting, it must play a key role in the magnetic field. We're now at the heart of the neutron star, which could be in the form of a solid core. Of course, this is only a hypothesis, as this inner part of the star is not accessible, and therefore not observable. However, certain characteristics of this precise part of the star can be estimated, notably by studying its mass and/or radius. For example, a neutron star with a radius of around 10 kilometers or 6 miles and a mass equivalent to 1.4 times that of the Sun would have a solid inner core 1 kilometer or 0.6 miles in diameter. where the neutrons would form a crystalline structure. It remains to be seen how the particles that make up the neutrons and protons, namely the quarks, reorganize themselves into this extremely dense environment. Do they form hitherto unknown combinations? Another peculiarity of neutron stars is their rotation speed. They generally have a rotation period measured in seconds. For some, this speed can be 30 seconds, while the most excessive ones rotate in just 1/100th of a second. To explain this more or less frenetic pace, scientists suggest that the neutron star, at the moment of its creation, recovers the rotational motion that the star previously possessed, conserving its angular momentum, also known as angular momentum. As a result, as the neutron star contracts, becoming smaller and smaller in size, its rotational speed can only increase. Since a star's motion is proportional to its mass, radius, and angular velocity, what would happen if our Sun were to turn into a neutron star? Its current radius, around 700,000 kilometers, would be reduced to just 15 kilometers or 9 miles. With its mass maintained at the same level, i.e., nearly 333,000 terrestrial masses, our Sun's speed would increase exponentially. If it currently takes 25 days to complete one rotation, it would then rotate. Hold on to your hat, at 1,000 revolutions per second. Although this example is very explicit, it will never become reality. The Sun isn't massive enough to pretend to end its days as a neutron star. It will turn into a banal red giant and end up as a white dwarf. A priori, all neutron stars rotate rapidly after formation. However, this speed tends to decrease as the star's magnetic field dilutes its energy. As a result, an older neutron star will rotate more slowly than a newer one. It seems that the observed rate of decrease in rotation speed is relatively constant, and above all, insignificant. Depending on their behavior, neutron stars are classified into several subcategories. Some of these stars stand out in more or less extraordinary ways. Let's take a look at Magnetars, some of the most exotic objects in the universe. Magnetars are characterized by extremely intense magnetic fields, producing high-energy electromagnetic radiation. In other words, X-rays and gamma rays. Apart from black holes, nothing in the cosmos generates such magnetic forces. The existence of magnetars was submitted in 1992 by two astronomers, Robert Duncan and Christopher Thompson. They established a relationship between the theory of intense magnetic fields and observations of gamma-ray sources. Observations of neutron stars with high Reynolds numbers, a dimensionless number used in fluid mechanics, demonstrated that these stars could generate extremely intense magnetic fields. While some neutron stars experience an increase in magnetic field strength as their rotational speed decreases, this is not the case for magnetars. This unusual characteristic is actually due to their very structure, and more specifically to their magnetosphere. But before we go any further, how is the magnetic field measured in general? Magnetic flux density is described in Tesla or Gauss units, with 1 Tesla unit corresponding to 10,000 Gauss units. The magnetic field at the Earth's surface corresponds to around 0.5 Gauss. Let's compare a few cosmic objects and their respective magnetic field strengths. The Sun's surface, depending on its activity, emits a magnetic field of around 3,000 Gauss. That of the supermassive black hole Sagittarius A is around 100,000 Gauss. That of the surface of a white dwarf is estimated at 1 million Gauss. Now imagine the strength of a magnetar's magnetic field, which reaches 100,000 billion Gauss at the very least. The magnetic field of any object is constantly changing. According to simulations, a magnetar's magnetic field could occasionally surge to 1 million billion Gauss. When it reaches a certain point between these two variables, it has a considerable impact on the star's outer layers. These, like a protective hyperdense crust as hard as or harder than diamond, see their structure deformed and fractured. When the magnetar's electromagnetic activity intensifies sufficiently, its neutron-based crust vibrates with such colossal intensity that it eventually shatters violently, just as the Earth's crust does during earthquakes. During these stellar tremors, which last between 0.1 and 3 seconds, and follow one another at an inordinate rate, X-rays and gamma rays are produced. These tremors, whose amplitude is estimated at 32 on the Richter scale, provoke veritable explosion eruptions that last a few days, or even weeks, before beginning a gradual decrease in intensity that can last several years before the star returns to its usual luminosity. Magnetars, described as the most powerful magnets in the universe, are the subject of much observation. A joint study by the Institute of High Energy Physics of the Chinese Academy of Sciences and the Kepler Center for Particle Physics and Astrophysics at the University of Tübingen has discovered the magnetar with the strongest surface magnetic field ever observed in the cosmos. The record-holding object is an ultra-bright X-ray magnetar located in the constellation Cassiopeia, 24,000 light-years from Earth. It is the neutron star, Swift GW200105 6+6124, studied thanks to the Swift Multispectral Space Telescope in October 2017. Already known to scientists as the Milky Way's only X-ray source of so-called ultra-bright objects, it has now revealed some of its characteristics, and not the least. It belongs to an X-ray binary system of neutron stars, the other star being a pulsar, which unfortunately is being devoured by its magnetic companion. And with good reason. Its magnetic field is 1.6 billion Tesla, or 16,000 billion Gauss. That's around 5 billion times more intense than the solar magnetic field. Under the effect of this monstrous gravitational force, the gas from the neighboring star has no choice but to fall towards the neutron star, forming an accretion disk. As the plasma in the disk sinks into the magnetic lines until it reaches the surface of the neutron star, it ignites, releasing powerful X-rays. The latter, due to the star's rotation, manifest themselves as periodic X-ray pulsation signals. This is why, This type of object is called an X-ray accretion pulsar. By carefully observing the spectrum of these X-rays, scientists discovered an electron-cyclotron absorption line and were able to directly measure the exceptional intensity of the magnetic field. This is the strongest magnetic field ever measured directly in the universe. To date, astronomers have recorded only 31 Magnetars. These objects are as fascinating as they are rare. One of them, located around 15,000 light-years from Earth in the constellation Sagittarius, and discovered in March 2020 by the Swift Space Telescope, with rather unusual behavior, is intriguing to scientists. This is Swift J1818.0-1607. Everything suggests that this is the youngest magnetar of all. The primary star is thought to have exploded into a supernova just 240 years ago, around the time of the French Revolution. This conclusion was reached by Australian researchers, who observed the star 8 times between May and October 2020. Initially, they found that its radio emissions were similar to those of a pulsar, with varying intensities. Then these emissions began to behave strangely, sometimes pulsar-like, sometimes magnetar-like. This short-lived phenomenon had never been observed before with any other magnetar. What's more, J1818's magnetic axis is not aligned with its axis of rotation, its magnetic pole being located just below the equator in its southern hemisphere. But that's not the last strange fact. It turns out that on the 1st of August 2020, its radio beam moved briefly at the object's northern hemisphere, suggesting that this star's radio pulses originate from loops of magnetic field lines connecting 2 closely spaced poles. Typical neutron stars, like our Earth, have north and south poles opposite each other on either side of the object. The observation of this unusual behavior, coupled with the star's data, a mass twice that of the Sun, a diameter of 25 kilometers, and a rotation period of 1.36 seconds, will have enabled astronomers to determine its young age. More common are neutron stars that emit a beam of radiation along their magnetic axis periodically, in the form of very brief pulses. Because this radiation fluctuates or pulses rapidly, a pulsar looks more like a cosmic lighthouse, at least in appearance, than a lambda star or planet, which shine uninterruptedly. Incidentally, for a time, these radio waves, emitted at a rapid and regular rate, were mistaken for manifestations of extraterrestrial civilization. The interval between pulses can range from a few seconds to several milliseconds. If a pulsar also shines continuously, the radiation emitted by each of the 2 poles of this rapidly rotating star gives the impression of luminosity at regular intervals. Many pulsars cannot be observed from Earth. To be perceived, a pulsar's cone-shaped emission must be directed briefly in our direction. Some 2,700 pulsars have been identified to date, most of them in the Milky Way, some in its star clusters. Only a handful of pulsars have been detected in the Magellanic Clouds. Among the most famous pulsars, we can't ignore the very first to be discovered in 1967 by Jocelyn Bell. It's PSR B1919 plus 21, located in the constellation Little Fox, which we've already observed earlier, just like the Crab Pulsar. But let's take a closer look at the different types of pulsar, whose characteristics depend largely on their environment and age. The most common are radio pulsars. These can only be detected in the radio range, thanks to their intense pulsed emission. This is why we no longer speak of stars in the strict sense of the term, but of compact radio sources. X-ray pulsars, on the other hand, are detected by their X-ray emission. This X-ray emission is not related to the surface emission, which is nevertheless very hot, at least several million Kelvin, but is generally the result of an energetic process triggered by the star's rapid rotation. A second theory suggests that these X-ray emissions are due to a colossal energy release, attributed to the accretion of matter from a second object, particularly in binary systems. Other pulsars, known as gamma-ray pulsars, emit, as you'd expect, gamma rays. Around 100 gamma-ray pulsars have been identified to date. Most objects of this type that evolve on their own are as rare as they are difficult to detect. They are usually found in binary systems. Isolated pulsars, whether X-ray or gamma-ray, are virtually all radio pulsars. Some X-ray pulsars are said to be anomalous, as they exhibit abnormally high X-ray emission, resulting in an extraordinarily strong magnetic field. What's more, compared with other pulsars, they have a very long rotation period, of the order of 6 to 12 seconds. They also undergo a very rapid deceleration phase, meaning they are probably very young objects, potentially due to their extreme magnetic field. In contrast, some pulsars have prodigious rotation periods, ranging from 1 to 10 milliseconds. These are the millisecond pulsars, sometimes referred to as recycled pulsars. Their magnetic field is one of the weakest, although close to 100 million Gauss. Often orbiting a companion star or white dwarf, millisecond pulsars are very old. Last but not least, Magnetars, the objects with unparalleled magnetic field strengths that we described earlier, are also a type of pulsar. Their disconcerting properties have yet to be fully explained. Are they singular objects, or are they just a temporary but usual phase in the evolution of pulsars? Understanding the stages through which stars pass also means being able to estimate their age. But how do scientists go about giving pulsars even an approximate date of birth? As we've just seen, pulsars rotate rapidly on themselves. Knowing that a pulsar's speed of rotation decreases over time due to its electromagnetic radiation, scientists are able to calculate the object's approximate age. Another method is to estimate the pulsar's kinematic age. In this case, after studying the object's immediate environment and defining the location of the supernova, researchers determined the time it took for the object to reach its current position. Many neutron stars have astonishing properties. We've already discussed Swift J818, which turns out to be a magnetar behaving like a pulsar, whose estimated age of just 240 years makes it the youngest pulsar yet discovered in the galaxy. But another pulsar is challenging astrophysicists with its strange behavior. PSR J0901-4046, also discovered in 2020, was detected after one of its pulses was picked up by the Meerkat radio telescope in South Africa. Because of its unusual behavior for a pulsar, it has long remained discrete. Unlike other stars in its class which rotate at very fast, even dizzying speeds, this one takes an inconceivably slow 75.88 seconds to complete one revolution. The slowest pulsar observed until this discovery completed a revolution in 23.5 seconds. For the researchers, this excessive slowness is more than a little disconcerting, especially as they thought that the radio emissions of neutron stars were a direct consequence of their rapid rotation. Another phenomenon makes this star totally baffling. It emits 7 different types of pulse, each with a different evolutionary history. Astronomers studying this type of star still have countless data to interpret, which should enable them to understand how they form and how they evolve. Above all, this latest find suggests that many stars like this slow pulsar are still hidden in our galaxy. As you know, in the cosmos, stars sometimes come very close together, forming binary systems. Some of these are natural laboratories for studying high-energy physics, general relativity, and stellar evolution. These are X-ray binary stars. These systems are composed of 2 different stars. One is an ordinary star, similar to the Sun, and the other is a neutron star, or in some cases a black hole. The neutron star or black hole, formed in the aftermath of a supernova, gravitationally attracts matter from its companion star, resulting in intense X-ray emissions. The material falling towards the neutron star forms a compact disk, from which friction generates such heat that a plasma is created, hot and shining in the X-ray range. 2 main types of X-ray binary star have been described. There are transient sources and persistent sources. The former are those that exhibit significant variations in luminosity, while the latter are stable, at least from the point of view of light emission. One of the most extensively studied X-ray binary stars is HER X1. Located in the constellation of Hercules, it is composed of a normal A-type star and a 1.5 solar mass neutron star. The latter gravitationally attracts matter from its companion, forming the inevitable accretion disk that emits X-rays. These very intense rays vary according to several time periods. Because of its rotation, the star pulses with a period of 1.24 seconds. It eclipses every 1.7 days, according to the period of the binary orbit. More importantly, HER X1's disk wobbles every 35 days, its line moving up and down as it rotates. The accretion disk of this neutron star thus has this strange feature. It wobbles as it rotates, influenced by winds within the disk. The study of disk winds fascinates scientists, who remain unsure of their origin. Is it the object's intense magnetic field that breaks up the disk before expelling some of the material outwards in the form of a wind? Or Is it the radiation from the neutron star that heats up the surface of the disk, evaporating some of it and sending it flying away like white-hot gusts? Astronomers are working hard to determine the origin of these winds and to understand how they influence their environment. The majority of neutron stars observed to date are part of a binary system. In most cases, their companion is a main sequence star, a white dwarf, a red giant, or even another neutron star. Scientists also suggest that a neutron star could just as well be in close proximity to a black hole. Should such a discovery ever be made, it would be a major breakthrough for astrophysics. In the course of their many observations, radio astronomers at the Parkes Observatory in Australia detected an unusual binary system in May 2003. This relatively close system, located in the constellation of Pope and only 2,400 light-years from Earth, consists of two stars, which up to now has been nothing out of the ordinary. However, in-depth study of this system, named PSR J0737-3039, has revealed two equally sensational features. On the one hand, this system is made up of two pulsars of at least 1.4 solar masses each, a feature that has never been observed in any other system. Secondly, these two components orbit each other at an extremely short distance, estimated at twice the distance separating the Earth from the Moon. In short, these two pulsars, which take it in turns to eclipse each other, remain within a cosmic handkerchief the size of our Sun. These observations were greatly facilitated by the fact that the system's orbital inclination is practically 90 degrees to the Earth, showing us its edge. When the first pulsar is detected, its signal shows a modulation with a period of 2.45 hours. For the researchers, this Doppler effect means that a companion is evolving alongside the pulsar under study, at a relatively short distance. This fact is confirmed by the next observation, which describes the two stars as pulsars, the first with an intrinsic rotation period of 23 milliseconds, the second 1,000 times slower, turning on itself in 2.8 seconds. This duo have what it takes to put Einstein's famous theory of general relativity into practice. According to this theory, orbital motion can generate a deformation of space-time, causing the axis of rotation of one of the two components of a binary system to oscillate, a movement known as precession. After 16 years of remarkably precise observations, the measurement of precession analyzed corresponds to the estimates delivered by the equations of Einstein's theory. Predictions of the energy loss associated with gravitational waves have similarly matched the theory. Based on these data, scientists estimate that the common orbit of the two pulsars is shortening by 7 millimeters per day, leading to an inevitable merger, which is expected to occur in around 85 million years. Neutron stars never cease to amaze anyone interested in them. Would you believe me if I told you that such stars host one or more planets? In 1992, the first planet, or rather pulsar planets, were identified by the Arecibo radio telescope on the island of Puerto Rico, the largest single radio telescope in existence until 2016. This discovery was made possible by chronometry, which enables us to measure the minute variations in pulsar periodicity and deduce the main orbital parameters of the objects responsible. The first planetary system discovered evolves around a pulsar in the Virgo constellation, approximately 2,300 light-years from Earth. Named PSR B1257+12, it has been known since 2007 to contain not one, not two, but 3 exoplanets, with a 4th yet to be confirmed, as well as a potential asteroid belt. In 1992, this announcement sent shockwaves through the scientific community, which had thought that planets could only be found near main sequence stars. The closest planet to the pulsar, Dragar, has a mass 50 times less than that of the Earth, and orbits the pulsar in just over 25 days. It is the smallest planet ever observed in the universe. The second, named Poltergeist, is the most massive, with an estimated mass 4.3 times that of the Earth. Farther away, it orbits in 66.5 days. Relatively close to the third planet identified, Phobetor, it is in close gravitational interaction with the latter, which is about 3.9 times more massive than the Earth. Finally, a 4th object has been awaiting confirmation since 1996. An initial study, later refuted, suggested the presence of a planet 100 times more massive than the Earth, and some 40 astronomical units from its star. However, an object does appear to be located in this region of space, causing disturbances to the system under study. For some, it may not be a planet but an asteroid, or even a comet. The second planetary system of this type is located in the constellation Scorpio, more precisely in the globular cluster Messier 4. In this binary system, composed of the pulsar PSR B1612-26 of approximately 1.35 solar masses, and the white dwarf WD B1620-26 of approximately 0.34 solar masses, evolves the Genesis planet, more commonly known as Methuselah. This exoplanet, known as circumbinary because it orbits a binary star, is about 2.5 Jovian masses in size. It takes around 100 years to complete a full orbit around its 2 stars. But its most spectacular feature is its age. 3 times older than our planet Earth, it could be as much as 13 billion years old. It is undoubtedly the oldest planet ever observed in the history of astronomy. The study of this exoplanet is of great interest to scientists. Formed shortly after the Big Bang, it is thought to be composed essentially of chemical elements, resulting from the primordial nucleosynthesis that took place during the first instance of the universe's life. Neutron stars have extremely varied but relatively stable rotational speeds. There are a few exceptions, however, and they sometimes undergo punctual and sometimes sudden accelerations. Astrophysicists call this phenomenon a glitch. This strange behavior is regularly observed in a neutron star just under 1,000 light-years from Earth. The Vela pulsar, visible in the southern sky, undergoes a glitch approximately every 3 years. Since this rotation anomaly seems to affect only a small population of pulsars, around 5% of them, the Vela pulsar, which experiences this problem with regularity, is particularly popular with glitch hunters. Observing these anomalies has enabled researchers to learn more about the star's composition. They found that at the moment of the glitch, the star began to rotate at a higher speed than previously observed, before slowing down to its cruising speed. They then deduced that the pulsar's center is actually made up of 3 components, one of which is a superfluid neutron soup located beneath the star's crust. Displacements within this hypothetical superfluid core would cause the famous starquake. When this neutron soup collides with the rigid outer crust, the celestial body is accelerated. Then, when a second mass of superfluid from the core hits the first wave, the star's rotation slows down. But these exciting observations raised a new mystery when it was observed that just before the glitch, the neutron star seemed to experience a slight slowdown before regaining speed. As yet, no explanation has been put forward, especially as there is no evidence that this phenomenon is related to the cause of the glitch itself. To understand the inner workings of such a celestial object, we must also consider its formation process. Neutron stars are among the densest celestial bodies in the universe, but knowing that they are merely the remnants of a dead star makes them all the more fascinating. Considered to be the little sisters of black holes, neutron stars can only form from certain stars, which must be particularly massive to make their final bow in a cataclysmic fireworks display known as a supernova. A star at the end of its life, over 10 solar masses, has a great chance of a second life as a neutron star. In other words, a dead star core. It all starts when a massive star reaches the end of its life, having burned all its fuel for the thermonuclear reaction. Some expand into peaceful red giants, but the most massive collapse in on themselves, exploding into a supernova. In this stellar disaster, the outer gaseous layers of the star are expelled into sidereal space. All that remains is the star's core, which no longer has enough energy to sustain the gravitational force. If its mass is less than 1.4 solar masses, it will take the form of a white dwarf. But in our case, its core, between 1.4 and 5.8 solar masses, generates energy in excess of the Chandrasekhar limit. As a result, electrons collide with protons, creating neutrons. The degenerate star eventually stabilizes. The remaining compact residue is then called a neutron star, with an average density corresponding to around 1,000,000 billion times that of water. Neutron stars are therefore born during explosive supernovae. While their future seems rather peaceful once the storm has passed, some of them experience other equally catastrophic events, notably stellar collisions. On August 17, 2017, Canadian astronomers were lucky enough to witness one of the most sought-after events in astrophysics, the explosive merger between two neutron stars. The two stars, located approximately 130 million light-years from Earth in the constellation Hydra, orbited each other at an ever-increasing speed, distorting the surrounding space-time, until the inevitable happened. the two massive stars collided and merged, triggering a gigantic explosion, which due to its remoteness could only be observed on this particular day in 2017. The event was first picked up by the LIGO and Virgo gravitational wave detectors in the USA and Italy respectively, and 2 seconds later, NASA's Fermi telescope detected a sudden burst of gamma radiation. For scientists, these two near-simultaneous observations led to a major discovery. For the first time, they were able to observe gravitational waves emitted, not by the merging of two black holes, but by the merging of two neutron stars. The signal detected proved to be much longer than in the case of black hole mergers, around 100 seconds versus a fraction of a second. Their second discovery was that this source of gravitational waves emitted light, which was observed for several weeks by 70 other ground and space-based observatories. This exceptional event, linked to two signals and named GW200105 became the first example of multi-messenger astronomy. For the first time in the history of astrophysics, such a cosmic event could be observed and confirmed using gravitational and electromagnetic waves. Because of its intensity, the explosion was catalogued as a kilonova, the first to have been the subject of real observations. Subsequently, scientists discovered that the new shape created by this fusion between the two neutron stars was, to their great surprise, perfectly spherical, as previous stellar explosion models had suggested a flattened, asymmetrical shape. The observation of this kilonova thus demonstrated that the theories and simulations carried out over the previous 25 years concerning these massive explosions were inaccurate. The error was attributed to the underestimated force of the explosions. Indeed, it was subsequently demonstrated that during the fusion process, the two neutron stars become part stellar giant before gravity causes them to collapse in on themselves. In this short space of time, colossal energy is released by radioactive decay in the star's core, allowing the explosion cloud to take on this unexpected spherical shape. Apart from the space-time undulations observed during this cataclysmic merger between two neutron stars, astrophysicists have made another discovery that should leave you dreaming. The collision of these two exotic stars has finally allowed them to solve the age-old riddle of how elements heavier than iron are synthesized in the universe. Remember, the heaviest element a star seems capable of creating is iron. Yet the cosmos is home to countless small, insignificant objects, at least at first glance, containing much heavier metals, such as silver, gold, and platinum. According to Enrico Ramirez Ruiz of the University of California at Santa Cruz, kilonovae, resulting from the fusion of two neutron stars, could well be the origin of an alchemy that creates these rare metals. According to the scientist, large quantities of neutrons are expelled during the cataclysm. These suddenly accumulate on neighboring heavy nuclei, forming heavier elements in a phenomenon known as the R process, or fast neutron capture. A single collision of this type could generate a colossal quantity of gold, equivalent to, hold on to your hat, a mass comparable to that of Jupiter. I leave it to you to imagine the enormous quantities of these singular atoms that could then sail with the cosmic tides in certain regions of space. As for the gold present on our Earth, it corresponds to the remnants of original gold atoms captured by our planet at the time of its formation, or deposited by asteroids that crashed into its crust. Other mergers between massive objects have been studied, notably that of two black holes whose gravitational waves were observed on September 14, 2015, thanks to the LIGO-Virgo collaboration, confirming the vibrations of space-time predicted 100 years earlier by Albert Einstein. Numerous other similar events have been detected. However, one scenario was missing, that of a mixed collision involving a neutron star and a black hole. Now, in January 2020, astrophysicists were fortunate enough to detect, just 10 days apart, two distinct signals corresponding to this precise pattern of mixed fusion. Again, thanks to the collaboration of LIGO and Virgo, but also Kagra, the Japanese gravitational wave detector, unusual gravitational wave events were recorded. On January 5, 2020, the signal name GW200105 came from a region of space around 900 million light-years from Earth, followed on the following January 15th by the signal named GW200115, a billion light-years away. Both turned out to be the result of collisions involving a large and a smaller mass, corresponding in both cases to a black hole violently absorbing a neutron star. This extremely rare phenomenon confirmed that beyond theory, a merger of this type could indeed occur. It also led to the conclusion that the neutron star, although highly massive, had been literally swallowed up by the black hole, which made short work of it without leaving the slightest crumb. Now we need to know the history of these two distinct, relatively massive objects. Did they originate from a pair of stars, one of which at the end of its life mutated into a black hole before engulfing its neighbor? Or did these two objects, originating in neighboring regions, eventually see their paths cross until the final explosive encounter? But let's return to a less chaotic region of space. I suggest you discover the neutron stars closest to our Earth. Known as the Magnificent Seven or the Seven Mercenaries, they were all discovered by the Rosat satellite, a German space telescope designed in the 1990s to observe low-energy soft X-rays. The first of these stars identified in 1992 was confirmed as a neutron star in 1996, followed by the other six. Located just 390 to 1,630 light-years from Earth, these stars generate powerful magnetic fields, and unlike their middle-aged counterparts, seem to remain extraordinarily quiet, giving off soft X-rays and ultraviolet light. This group of stars is of great interest to astrophysicists. They provide an ideal laboratory for unraveling the mystery of dark matter. Never observed by scientists, we still know nothing about the properties of this matter, for which there is nevertheless substantial astronomical evidence of its existence. For now, science suggests that dark matter could be a stable, electrically neutral subatomic particle of unknown mass. This theoretical particle is incidentally called an axion. Scientists are therefore interested in the Magnificent Seven that emit soft X-rays. Relatively silent and very quiet, these stars represent a unique opportunity to search for small, unexpected bursts of other forms of light, which could be linked to the presence of axions. By interacting with the intense magnetic field enveloping the neutron star, these could be converted into photons, or high-energy X-rays, i.e., hard X-rays. So far, astronomers have revealed that 2 of the 7 stars emit significant amounts of hard X-rays, while the others seem to emit them in much less obvious ways and in varying quantities. This suggests that axions may be the source of these hard X-rays. However, these axions have not been observed. This is still only a hypothesis, which needs to be put into practice. In fact, many laboratories are trying to reproduce this scenario. Who knows? One day soon we'll be told we've solved the mystery of dark matter, not in space, but on Earth. Another fact about the Magnificent Seven cannot be overlooked. It turns out that these neutron stars would have an 8e companion. Discovered in 2007, this neutron star, located in the Little Dipper constellation, at an estimated distance of between 250 and 1,000 light-years, has been christened Calvera. Located outside the galactic plane, its configuration remains a mystery. It is one of the few neutron stars to evolve on its own, with no companions or supernova traces in its vicinity. Could it be the remnant of an exploded star in our galactic disk? Researchers don't yet have an answer, but say it's probably the closest neutron star to Earth known to date. Its proximity and very high X-ray luminosity make it a prime target for studying this type of unusual star. Numerous research programs are underway to determine whether it emits pulses, either in X-rays or in the radio spectrum. Some neutron stars display ever more extraordinary characteristics. This is particularly true of J0740 plus 6620, whose discovery in 2019 has unsettled American astronomers. This pulsar is so massive that scientists thought no such star could exist. This small neutron star, with a diameter of no more than 30 kilometers or 20 miles, single-handedly defies the laws of physics, boasting a mass of 2.3 solar masses, or 700,000 times that of our Earth. Its mass, calculated thanks to the presence of a white dwarf companion, is so great that the star should be in the process of collapsing into a galactic black hole of several billion solar masses. However, this is not the case. This neutron star, though microscopic on the cosmic scale, should enable researchers to study the limits of stellar mass and further unravel the laws of the universe. One of the most unusual neutron stars is J1008-57. This is an X-ray pulsar in the accretion phase, detected in 1993 by a NASA gamma-ray space observatory. Its strangeness lies in its surface magnetic field, which is the strongest ever detected. It is around 1 billion Tesla, tens of millions of times stronger than a magnetic field that can be created in a laboratory on Earth. This exceptional peculiarity was discovered in 2020 by the Chinese Space Agency, which was quick to share this finding, challenging the known upper threshold of cyclotron resonant scattering. Neutron stars really are the stars of extremes. Although they are among the densest objects in the universe, one of them has once again stumped astronomers with its mass. It has not turned out to be monstrous, but on the contrary, has a value well below that predicted by theory. Named J1731-347, the star appears to be a neutron star in the afterglow of a supernova, 8,150 light-years away, with a mass of just 0.77 solar masses and an estimated radius of 10.4 kilometers or 6 miles. Until now, the lightest neutron star had a mass equivalent to 1.17 times that of the Sun. This once again challenges our understanding of stellar physics. Scientists are still trying to work out whether this is indeed an extremely light neutron star or a star of quarks. If the former, how could it have formed? Could a large part of its initial mass have been extracted from the core during the explosion due to the presence of its companion? Or could this star actually be a strange star, that hypothetical type of star, very dense and composed essentially of strange quarks of unknown composition? If so, it would be the first star of this type to be discovered. Indeed, strange stars are only a theory at the moment, and would lie on the borderline between a neutron star and a black hole. Finally, we can't look at neutron stars without considering the case of Betelgeuse, the well-known star in the Orion constellation that forms part of the famous Winter Triangle alongside Sirius and Procyon. Admittedly, it's just a red supergiant with an estimated mass of 15 solar masses. But this dying star, located just 530 light-years from our Sun, whose size is equivalent to 700 times our Sun, and whose luminosity places it 10e position after our Sun in the night sky, has been arousing the curiosity of astronomers for many years. It could well be nearing the end of its explosive life. What's more, a significant drop in its brightness was noted at the end of 2019, lasting several months before it returned to its previous appearance. While not all scientists agree on the reasons for this punctual dimming, the fact remains that the star goes through pulsating phases during which its size and luminosity fluctuate. Betelgeuse seems to be showing warning signs that the supernova that will give it the final coup de grace may be just around the corner on a human scale. For some astronomers, Betelgeuse's core must be in the final stages of carbon fusion. Given that this stellar explosion, which must be visible even in broad daylight, will take 530 years to be observable from Earth, it remains to be seen whether we will have the opportunity to admire it in our lifetime. Our interstellar journey is coming to an end. Fascinating neutron stars are beginning to reveal the secrets of matter and gravity. The result of the explosion of massive stars, releasing enormous quantities of energy and chemical elements, these stars display an uncommon cosmic alchemy. Through an exceptionally violent nucleosynthesis process, they are responsible for the formation of the heaviest of the 118 stable elements known to date in the periodic table. Above all, in their final cataclysmic burst, these stars eject elements such as carbon, oxygen, and iron, which are essential for the formation of life. Some of these elements, after drifting through the cosmos, end up accumulating on planets in a totally random fashion, at the whim of cosmic movements. This is how biological diversity probably developed on our Earth, itself bombarded from the moment of its formation by a quantity of elements emanating from these explosive ends of life in a more or less close environment. We can therefore assume that neutron stars very probably played an essential role in the formation of life on Earth, and why not elsewhere in the universe? After all, why should our Earth be the only one to have benefited from this miraculous and hazardous evolution? Do you really believe that our life-bearing Earth is unique in this infinite cosmos?